Okay, in Lesson 8A, we're going to discuss something called a discrete probability model. And we'll talk more in one of the other later lessons about the difference between discrete and continuous probability. For now, just know that discrete means probability involving counting things, which is what most of the probability we've been talking about in the lessons up till now have been. So there are multiple models that are useful because we can kind of pre-work out the way they work, because that situation occurs frequently enough that it's just better to kind of pre-solve the problem. So that's what these probability models are. They're basically pre-solved problems that work in a variety of situations. So when we see that situation, we can go right to this model to calculate the probability, instead of going back to the foundational ideas in lessons 1 through 7 to calculate it by hand every time. And this lesson, 8A, is going to focus on the most commonly used of these models, which is called the binomial probability model. Okay, so to investigate this, let's consider this situation. Students at a particular university voted 60% of the time in the most recent election. So if 3 students are selected at random from this university, what's the probability that exactly 2 of them voted in that election? Okay, we could represent this situation with a tree diagram where I'm using Y here to represent that a student did vote and N that they didn't vote. So this first branch is the outcome of the first student, then the second student, the third student. Right, here are all the branch probabilities. If there's a 60% chance of an individual student voting, then that means that the yes probabilities of all the branches are 60%, and the no probabilities would be the 40% chance, the complement of 60%. Okay, and only 3 of the N nodes represent exactly 2 students voting. This case here, where the first student voted and the second student voted and the third student didn't, Y, Y, N. This one, first student voted, second student did not, third student did, Y, N, Y. And then this one, first student did not, second and third students did, N, Y, Y. All of the other cases represent some other number other than exactly 2 students voting. So, since the first student and the second student and the third student have to vote in a particular way, the probability of the N nodes we know are end cases, so we would multiply the probabilities. So, for example, the probability of Y, Y, N would be 0.6 times 0.6 times 0.4. And the probability of Y and Y would be 0.6 times 0.4 times 0.6. Okay, but because we can have 2 students voting in the first way or the second way or the third way indicated in green here, these 3 ways, this or this or this, that means that if we want the total probability of exactly students voting, we have to add those probabilities, because we know that when we have OR cases that are disjoint, and there's no way you can be at more than one endpoint at the same time, we just add the probabilities. So the probability that exactly 2 voted, it would be the first plus the second plus the third term there. Okay, so I want us to look at and notice a couple things about the terms. First of all the terms involve 2 yes probabilities and 1 no. So we could write each term as 0.6 squared times 0.4, 0.6 squared times 0.4, 0.6 squared times 0.4. And there are 3 of these added up. So I could instead think of it as the number 3 times 0.6 squared times 0.4. And that probability is 0.4320. So about 43% chance that exactly 2 of the 3 students would have voted. Okay, why are there 3 terms? Well, if there are 3 students being asked if they voted and 2 of them answered yes, what we really want to know is maybe how many ways could we choose the 2 of the 3 to be the ones who said yes? Well, that would actually be a combination, right? We're choosing some students out of a group. It doesn't matter what order we choose them in. We just get a list of the students who voted, which ones, right? So if we think of it as of the 3 spots, how many ways are there for me to choose the 2 that voted yes? That would be 3 combination 2, which turns out to be 3. So this 3 number here is actually could be thought of as out of 3, choose the 2 spots for the successes, the people who voted. So given that, we could analyze the probability this way. We could just say, well, the probability of yes is 0.6, and there are 2 students that have to vote yes, so there's 2.6 probabilities. The probability of voting no is the other 40%, and there's 1 student that would have to vote no, so there has to be 1 no probability, 0.4. And then we have to figure out, well, which of the 3 students are the ones, which of the 3 are the 2 that did vote. So that would be there's 3 choose 2 ways to do that. And we could just take 0.6, 2 of those multiplied with 1.4, and then multiply by 3 to account for the different ways that they could be ordered. Okay, so for us to use this pattern, there's a whole class of problems that we can solve using the same exact tactic. But these things on this list have to be true. You have to have only two outcomes, something that can be called yes or no, or success or failure. In this case, the yes is that the student voted, and the no is that they didn't vote. The probabilities have to be constant for each trial. You can't have probabilities that are changing as we go from trial to trial. And the probabilities of the trials must be independent of each other. In other words, whether one student voted or not shouldn't in any way depend on the previous student. And, in this case, we have to have a fixed number of trials. And here we're talking about asking exactly 3 students. So if those 4 things are true, then we have this specific situation that could be solved with this pattern. The number of successes, number of ways to make the successes, probability of successes, and probability of failures. So the first 3 items on that list define what are called a Bernoulli trial, or a Bernoulli setting, named after a famous mathematician who first proposed this. The only 2 outcomes criteria, probabilities have to be constant for each trial, probabilities of the trials have to be independent. If we have that situation, it's known as a Bernoulli trial problem, or a Bernoulli setting. Okay, the last item, having a fixed number of trials, further defines this more specifically as a Bernoulli trial binomial setting. Okay, so specifically, if we have a fixed number of trials, the 3 students in this case, we can call it a binomial setting. The reason it's called a binomial setting is because of the format for the pattern. If you look at that format that we have, 3 choose 2, 0.6 squared times 0.4, it looks the same as a term in a binomial expansion. If you look at, for example, the binomial a plus b to the 3rd power, that can be expanded into 4 terms using the binomial theorem. And every term has a number from Pascal's triangle, which is really a combination. And then it has the left side of the binomial raised to an exponent times the right side raised to an exponent. And there's various patterns for counting up and down. But if you look at the pattern of that, that looks the same as the pattern for our tree diagram that we analyzed before. And so for that reason, this particular model is called the binomial model. Okay, so for Bernoulli trials with a binomial setting, we can use the binomial probability model, which we can state more generally this way. The probability of having exactly k successes out of n total trials is n combination k times p to the k power times q to the n minus k power, where p is the probability of success on a single trial, and q is the probability of failure on a single trial, which would be 1 minus the probability of success. Okay, so let me just solve the problem over again, this time without doing the diagram, just to show you how we could immediately use the model. We can say, okay, students at a particular university vote 60% of the time. If 3 students are picked at random, what's the probability exactly 2 voted in the election? So we could ask, does it meet the criteria for being a binomial model? Are there only 2 outcomes? Yes. Success is that a student voted. Are the probabilities constant? Yes. The probability of voting is always 0.6. Are the trials independent? That's likely to be true as long as the students were randomly selected. It wouldn't be true if you had a situation like, say, we selected 3 people walking together towards the student union. Then, if one student voted, the person next to them might have the same political views. So, that wouldn't be independent. But if we really did randomly pick 3 students from anywhere in the university, it's very likely that the probabilities don't depend on each other. And then, finally, do we have a fixed number of trials? Yes, n equals 3. Right? So that means that we have the criteria to meet the binomial model, so we can jump immediately to solving the problem with the binomial model pattern. That the probability of exactly 2 voting out of 3 students would be 3 combination 2 times the 0.6 probability squared times the 0.4 probability 3 minus 2. 1 student left to not vote. So that would be 3 times 0.6 times 0.6 times 0.4, which is 0.432. No need to do the tree diagram. No need to remember the and or rules. It's just a pattern that works in this special case. But this special case happens actually quite frequently. Now our calculators make this even easier to calculate because we can do this in a single step. There is a function called binomial PDF that we can give 3 values to: the total number of trials, the probability of success, and the value. Sometimes it's called x. In the calculator it's identified as x. It's the number of successes. So in this case we would do binomial PDF out of 3 trials. Probability of voting is 60% of exactly 2. Let me show you where that is in a calculator. If you have a TI 84 or 83, then you see where it says distribution, D-I-S-T-R, up there in colored lettering. You can press your color key, the second key, and the variables key to get to the distribution menu, and scroll way down here, past the bottom of the screen. There is Binomial PDF. And so if you click it, one of two things will happen. If you have a newer calculator, it'll bring up a little entry screen where you can enter the number of trials, 3 students, the probability of voting, 0.6, and the X value, we want the probability of exactly 2 students voting, and then hit paste. If you don't have that screen, it will just say Binomial PDF with a parentheses, and you have to remember the order and enter them in that order. So you would press 3, and then you have to manually insert the comma, which is this key right here. So 3, comma, 0.6, comma, 2, and then close the parentheses and then hit enter, and it'll compute 0.432 directly in a single step. So very nice. This model occurs so frequently that we have a dedicated function for it in the calculator. Okay, so examples of Bernoulli trial binomial setting problems. Let's say we're tossing a coin 10 times and we want to find the probability of getting 3 tails. That would qualify as a binomial model problem because coins have no memory. The probability is independent. Whatever the probability of getting heads is, usually be 50%, or tails would be 50%. That's going to be constant, right? We have only 2 outcomes. You can get a tail or not get a tail, right? And we have a fixed number of trials. We toss 10 times. The second one, polling 8 voters, asking whether they're Republican or not, and finding the probability of having 3 Republicans. So we have a fixed number of trials, 8 voters. Presumably there is some probability in this population of being a Republican, right? And as long as we ask a random sample, the probability would be independent from person to person. And then the yes or no criteria, right? There are more than 2 parties, Republican, Democrat, Independent, and various other things, right? But if we talk about the probability of being a Republican or not, then we've divided the problem into Republican as the yes case and not as the no case. Anything other than Republican is considered no. And so this is, in fact, a Bernoulli trial binomial setting problem. Test with 12 questions. Probability of getting a question correct is 70%. Finding probability of getting exactly 9 questions correct. Right? We can either get the question correct or we don't get it correct, and that means it's a yes or no situation. We have a fixed number of trials, 12. The probability of getting correct is 70%. This is definitely a binomial problem. Rolling a die 20 times, finding the probability of getting a 5 exactly 7 times. There are 6 outcomes if I roll a die, but if I talk about the probability of getting a 5, 5 is a specific yes case. The no case would be anything other than a 5. So in fact it is a yes or no situation with a fixed number of trials, right? And we would be finding the probability. Okay, so let's take one of those, the flipping a coin thing, and we'll investigate some other properties of binomial model a little further. Let's say that I flip a fair coin 10 times. What's the probability of getting exactly 2 heads? Or maybe separately, the probability of getting exactly 8 heads, or the probability of getting exactly 5 heads? So this is definitely a Bernoulli trial binomial setting, so we could quickly find these probabilities using our calculator function. If the coin is fair, then that means the probability of getting a head on a single toss is 50%. So if I wanted to answer the question of the probability of getting exactly 2 heads, I would use Binomial PDF 10.52. Out of 10 heads, out of 10 tosses, 2 being heads with a 50% chance of getting heads. Let me do that one in the calculator real quick again for you. Distributions, scroll down to Binomial PDF. There it is. Make sure you pick the PDF version. We're going to talk about CDF in a second. 10 flips of the coin, 50% chance of getting heads. We want the probability of getting exactly 2 heads. And so that would be 0.0439. And the probability of getting 8 heads would be 0.0439. The probability of getting 5 heads would be 0.2461. So the probabilities might be the same or they might be different. Right? It just depends on the situation. And actually in the later video we're going to talk about the distribution of these probabilities. Okay, let's actually look at the probability of all the possible outcomes. In other words, let's build the complete probability model. If we flipped a coin 10 times and we're interested in the number of heads, we could define x to be our variable that represents the number of heads we get on a particular experiment of 10 flips of the coin. This x, which we usually use a capital letter for, is what we call a random variable, because unlike a regular algebraic variable, which is a placeholder for a specific value, this variable is expected to vary and have a different value for each of our experiments. So it's a little bit different than a regular variable, but you can still think of it as a placeholder. It's just a placeholder for something that we expect to vary around. Okay, so we'll use our probability model here, right? X, the random variable, represents the number of heads that we get in an experiment where we flip the coin 10 times. And what we've got listed here is a listing of the sample space of all possible values of the random variable. We could have 0 of them of the 10 be heads, or 1 could be heads, or 2, or 3, all the way up to 8, 9, or 10 could be heads. All 10 could be heads. Below that, we can put the probabilities of each of those exact situations happening. And for each of them, we would use a binomial PDF function. So for example, if I wanted to find the probability of having exactly 4 heads, then it would be binomial PDF out of 10, 50% chance of having heads, comma 4. And that one would be 0.2051. Right, so I could do a binomial PDF for every individual case. Okay, well, what if I wanted to find the probability that up to 2 tosses were heads? This is actually an OR case compound event. We're successful if we get 0 heads, or 1 head, or 2 heads. Right, and we know that in OR cases we would add probabilities, right? So we would add the probabilities of these 3 cases. We would add the probability of 0 heads, the probability of 1 head, and the probability of 2 heads. And if we add, we could use the binomial PDF function for each one of those cases. This is the probability of having exactly 0 heads, the probability of exactly 1 head, probability of exactly 2 heads, and they add up to a total of 0.0547, a little over 5% chance. Okay, because this particular situation occurs so frequently, our calculators provide us with another function that does that in a single step. So the binomial PDF, the PDF part, it actually stands for probability distribution function, because it shows how the probability is distributed across all of the different outcomes. There's another function right below it in the calculator listing that's called binomial CDF, binom CDF. That stands for binomial cumulative probability distribution function, because it provides the cumulative total of all the probabilities starting at 0, counting up to and including the number that you put in there. So binomial PDFs give me exact probability values for exact cases, but if I want to find the probability of 0, 1, and 2 altogether, the cumulative total, I can use the binomial CDF function and say out of 10 trials, 0.5% chance of having a head up to and including 2. And I can get that calculated in a single step. Let me show you where that is on the calculator. If we go here, second, vars, and I scroll down here to binomial CDF, right below binomial PDF, there's binomial CDF. It's got the same entry structure. So 10 trials, 0.5 probability of having a head, having up to 2. That's going to add 0, 1, and 2 cases together, and that gives me 0.054 rounds to 7. All right, so we have a second probability function that we can use for anything which is kind of to the left of a boundary value. Okay, one more scenario. What if I wanted to find the probability that at least 3 of the tosses were heads? Right, there isn't a calculator function for this, but we actually don't need it because we can use the CDF function. So if I wanted to find the probability that at least 3 of the tosses were heads, that would be all of these cases from 3 on up to 10. Right, but if I add up all of the probabilities for all the outcomes, that has to add up to a total of 1, right? Because 100% chance that something's going to occur. So that means that the probability to the left of some boundary plus the probability to the right of some boundary is adding up to 1. So if I want to find the probability to the right of some boundary, all I have to do is take 1 and subtract the probability to the left of the boundary. Right? So the probability of at least 3 heads is equal to 1 minus the probability of up to 2 heads. So I would just say 1 minus the probability to the left of that 3. So that would be 1 minus 0.05468, which is 0.9453. Okay, so just to summarize this, many problems actually fit into this situation. Bernoulli trial binomial setting. The Bernoulli trial part is that if you have only 2 outcomes and you have probabilities that are constant for each trial, and the probabilities are of the trials are independent from each other. And then that's the Bernoulli trial. And then if you also have that you have a fixed number of trials, that makes it a binomial setting. So that means you can write the outcomes of a random variable that lists all the possibilities from 0 up to the maximum number. And then if you want to figure out an exact case, like for example the probability of exactly 2 heads, then that means you'll use the binomial PDF function here. The total number, probability of success, and then the value that you're looking for. If you want what I call a left side case, say the probability of up to 2 heads, which would be everything from 2 on down, then you can use the cumulative version, binomial CDF, 10, 0.5, 2. If you have a right side case, like the probability of at least 3 heads, then if we put the dividing line here, this is going to be 1 minus this side. So we would take 1 minus the binomial of from 0 up to 1 less, the 2. Okay, so that's a summary of just the binomial model. Now if you go on to the next video, we're going to present 2 other models that are different in a couple of different ways. One's called the geometric model and one's called the Poisson model, and then we'll kind of summarize some things about that. Then there's a third video in this series that talks about how these probabilities are distributed across the outcomes.